In this lecture, we emphasize the link between number theory and geometry. I believe that we cannot dissociate number theory from geometry, and if we are patient enough, we'll see how this is applied to cryptography. In this first part, we start with the simplest one-dimensional geometric shape, which is a line. Let L be the line on the plane defined by the equation 3x plus 10y equals 1, as you can see here on the screen. We would like to find integral and rational points on it. It is obvious from the equation of L that it has infinitely many rational points. Indeed, we can write L in the following form: y equals 1 minus 3x divided by 10. This implies that the point P of coordinates x 1 minus 3x divided by 10 is a point on L with rational coordinates. For instance, if we take x equals 1, we find that we have a point P1 of coordinates 1 minus 1/5, which is on the line. Actually, we can see it here. It is this point, 1 minus 1/5. Now the good question is, are there any integral points on our line L? Or said in other terms, points P such that x and 1 minus 3x over 10 are both integers. If we take a close look at the graph of our line, we see that this point here of coordinates minus 3, 1, and this second point here of coordinates 7 minus 2 have both integral coordinates. Actually, all the integral points on this line are of the form 10k minus 3 and minus 3k plus 1. For k equals 0, for instance, we find the point minus 3, 1, and for k equals 1, we find our point here, 7 minus 2. We can verify by straight calculations that this is actually true for all integer k. We have here 3 times 10k minus 3 plus 10 times minus 3k plus 1 equals 30k minus 9 minus 30k here plus 10, which is actually 1. This means that all points of this form are integral and lie on L, but in order to prove that every integral point on L is of this form, we will need the theory of divisibility of integers that we will encounter in future lectures. From this example, it is obvious that on any line with integral coefficients, there are infinitely many rational points. We might actually expect to find infinitely many integral points on such lines, but this is wrong in general. We show this in an example. Let L prime be the line in the plane defined by the equation 3x plus 12y equals 1, as you can see on the screen. As we said before, L prime contains infinitely many rational points given by P of coordinates x 1 minus 3x divided by 12. Now, are there any integral points on our line L prime? The answer is no, and it's actually easy to see that we have a contradiction by writing L prime 3 times x plus 4y equals 1, which means that if x and y are both integers, then 3 divides 1, which is not true. Thus, we have proved that our line L prime cannot contain any integral point. Let us take some seconds to think about what we have done. Both of the examples of L and L prime show two lines that behave differently when we look for integral points. Indeed, L passes through infinitely many integral points, while L prime intersects none of them. Interesting, right? Why do they behave so differently? The reason, as we shall see in depth in future lectures, is that GCD of 3 and 10 is 1. GCD here refers to greatest common divisor, and the GCD of 3 and 12 is 3. More generally, if L is a line defined by an integral equation ax plus by equals c, a, b, and c here are integers, then if we denote d the GCD greatest common divisor of a and b, we can show easily that if d does not divide c, then L does not contain any integral point. In fact, this is true because we can write a as certain integer a prime times d, and b as a certain integer b prime times d, and we get as an equation of our line L d factors a prime x plus b prime y equals c, which means that d must divide c, otherwise there won't be any integral point. We will see, however, in future lectures that the fact that GCD of AB is equal to 1 ensures that L contains one integral point and actually infinitely many of them. The first part of lecture 2 ends here, and we will investigate in the second part integral and rational points and more complicated geometric shapes. Thank you for listening.